good afternoon. My name is Francisco Weber. I come from Austria. My company is called Cortical.io, and we are working in the field of machine learning, which I will show you today. And just one sentence to start with to give a connection to robotics from our perspective. So in our experience, the AI effect or the machine learning effect is important for robots because it allows us humans to better understand what they do and what they plan to do. And on the other hand, as we have seen recently with the large language models, these techniques will allow the robots to better understand us. And I think one of the strongest outcomes will be the fact that what we know as chatbots today will become a new generation, a new kind of human interface with the computer in general. So I hope I know how this works. Yes, all of us remember this moment 2 years ago when we first noted that the computer actually speaks back. In the sense, he spoke back to us as would another human do. That was basically the start of the most recent AI wave that came over us in many different disciplines. And it actually beat all records. I mean, just to name one most characteristic, it took ChatGPT only 5 days to reach 1 million users, which has not been accomplished by any other offering that we get from the internet. So, but what in my opinion, and language has always played a big role in my approach to machine learning, what is the real big step is that once and for all we got the proof that language is actually computable. So for many, probably 100 years, the specialists have been discussing to what degree it was necessary to have a human, literally a human brain to be able to understand and produce language in a way that is relevant for us humans. Definitely ChatGPT, however, it actually did it, but it was able for the first time to sound and feel like talking to a human. That was too fast. What was interesting is, although there is a lot of science in this whole approach, what was interesting to me at least was in the first moment, it rather looked or sounded to me like a cooking recipe and not so much like a formula like we are seeing that at the output from physicists and other natural science people. And what was also very relevant, and in the beginning we were not so much aware of it, but it is possible to improve an AI by simply adding more of everything. So it's basically a brute force approach, which actually became very quickly a characteristic of this whole situation. And by the way, we know where brute force in technology can lead in the end. It starts to use up resources to change nature. I mean, we are suffering currently the change of the whole ecosystem on the planet after a couple of thousand years of technology development that we have produced as humans. And what is also a standard is our inability, I would even say, to properly predict where certain technologies will evolve later on. And as currently the evolution of technologies and discoveries gets faster and faster, we are incapable of saying where what we call AI today will lead us in a week. So one thing is sure, and I do agree with many analysts on this, that AI in general will become a commodity. It has to become a commodity. I remember I'm old enough to have carried around the first mobile phone that was actually a small suitcase. Nowadays, if you look, I can have it here in my breast pocket. So I think it might not look like this, but I think, and we have seen this from the previous talk, AI will just mix among us humans and become part of our reality. But if we extend this whole concept of brute force, we know that there is another phenomenon that mostly from the economic side comes in, is that when you get better as you get bigger, it becomes, of course, more and more expensive to become bigger, which in the one of the possible ways this plays out is that you have one provider in the end who provides basically the AI for everybody. And I'm not sure if this is actually good, if we should go in this direction. And so one way of preventing such an outcome is precisely to make it a commodity and to make it small enough to be able to distribute it across the society and the businesses. So just a rough ballpark number. Currently, GPT-4 is estimated to have used about 5 million kilowatts to be rendered once. We use as humans during a lifetime, let's say of 30 years, our brain uses about 5,000 kilowatts. So we need to become like 1,000 times more efficient in order to even play in the same ballpark as the human brain does. When we apply a trained model in AI, we use about 1 watt to come up with the recipe of pancakes. In highly efficient system, commercial systems today, you still use some 100 watt hours to do the same thing using ChatGPT. So how can we improve those large language models? And I take large language model here as like the biggest class, but you can apply this to any kind of machine learning. We can improve things by just throwing more compute at it. That's what the current strategy is in building larger and larger GPU clusters that use more and more energy and so on. We can use bigger algorithms. We can add more parameters to our models, which again makes everything more expensive and use more energy. But there is a third way that basically very few people have ever thought of so far, which is improving the representation. Just imagine if you listen to an audio file that has been sampled with, let's say, 4-bit resolution, you will hardly understand anything because the representation is so poor that even a human brain, with all the gadgets that we have to understand language, we will not be able to understand anything. If we use a 16-bit CD quality, as we used to say, sampling of the audio, which is a much better representation of the actual information, it will be very easy to understand and to learn from things that we hear. So that brings me to precisely the region where we are active as Cortical.io, which is actually representation learning. So we don't try to come up with another way of doing machine learning, but what we try to do is we try to improve the representation of data, whatever the data is, and make the probably existing machine learning model that you use less energy, render much faster. For example, for sensors, we are able to process the data in real time on embedded platforms even. And the main way how we do this is that we represent data as two-dimensional binary patterns. That's how supposedly the human brain is doing this. And we try to capture in this representation the semantics of the system, of the data space that we're actually modeling. So this allows not only to have a more efficient way of processing, but it even allows you to use other types of processors, things that are not CPUs maybe. So we've been working a lot with programmable hardware that basically can parallelize down to the binary level the data that is processed, and we managed to have orders of magnitude speed improvement with this. So I will give you a quick fly-through through the universe of semantic folding. That's the representation technology that we have invented, let's say, or I would rather say discovered, because I think it's a very generic way of processing data. It was originated by a neuroscientist in California called Jeff Hawkins, who actually developed a theory on how the human neocortex, basically the place where the thinking, the processing actually happens, how the computational system behind this actually works. And when I joined him in 2008 around with this work, I was mostly interested in finding a way that was also a biologically viable way of rendering the input data for these kind of networks that he was describing. So basically how this works is that we do some machine learning based on reference data. That's what we do basically constantly. We constantly add the impressions that come from our sensory organs into a representation / model of the world. And that reference data is always used to encode any new data that comes in. So what we are able to do after a relatively quick training of not so much data as we are used today in the large language model area, we come up with a system that we call a semantic space that is able to encode any information that from there on we send to the system into a semantic fingerprint. That semantic fingerprint depends, of course, heavily from the reference information that we train it on. So here you see an example of language. I will mostly use examples from language, but what you see can be applied to any numeric or categoric information in the very same way. So in terms of language, you have the term cholecystitis, which is a medical term, and you see it on the upper side, you see the fingerprint that is rendered from or for this word when the system was trained on Wikipedia. So obviously that word occurs a couple of times in Wikipedia, but it's kind of a sparse definition that you see there. If we train the same system on professional information from the National Library of Medicine, you see that we basically get the same pattern, just expanded with much more detail. And that is what is key to this whole semantic fingerprinting approach. Everything becomes comparable to everything. And that basically corresponds to what we do with our human brain when we think. In fact, we compare constantly stuff that we perceive with stuff that we have stored. That's how we think as humans. To look a bit closer to these semantic fingerprints, you will see, again, things look much clearer if you use language as a base pattern to it. What you can see is that depending on the region where you look at the bits that are set in the fingerprint, you have different contexts, different meanings that are located in a two-dimensional map. And every word, basically, is rendered as a pattern of all of these. In this case, there are 16,383 contexts that have been computed, and every word in my reference set gets rendered into a bit pattern telling me where are the contexts for a given word. And as a consequence, as we get sparse vectors out of this, so this is kind of a mathematical feature of sparse vectors, is that they can be added together without actually losing information. And that's the way how we get from understanding the meaning of a word to understand the meaning of a sentence. So it's very simple. We can, if we have a sentence, we can look up every individual word. We can convert the word into a fingerprint, and then we can add, means union in the binary sense, all the fingerprints together, and what we get is a fingerprint for the whole sentence. And just as a footnote, you see here the sentence is organs and pianos are musical instruments. Organs in English could be either a musical instrument or it could be the medical sense of the term. And you see that the aspects in the word organ that are specific for the biological function, they get just eliminated by aggregating those words because no other word puts an emphasis on these aspects of the word organ. And that basically solves an old problem in natural language processing, which is disambiguating words. Every word has several meanings, and how do we do to figure out which meaning is the actual meaning? We do this by putting the word in a sentence, and suddenly, as a byproduct of putting it into a sentence, based on a mechanism like this, we get an implicit disambiguation of any word. And that is fundamentally the reason why we do all of this. We want to convert data, in this sense, in this case here, the data is text, into something that we can very efficiently compare. So if we have these two fingerprints, and by the way, they are specifically in the size of 128 times 128, we can compare them by simply superimposing them and counting the overlap. How many bits are the two fingerprints actually sharing? And the more bits they share, the more similar the data is that was sampled in the first place. And this is something where you don't need to calculate any model or process the whole thing. You just need to render the two bits of information into a fingerprint and then count the overlap between the two. And you see phrases like done deal and signed contract, they don't share a word, but still have a very strong overlap, as when we change one side to Star Trek, which is not matching, the overlap drops to a much lower score. What is interesting is that this kind of representation is even independent from the language that it originates from. So after rendering semantic spaces in different languages, we find out that the very same concept, philosophy in English, renders nearly the same. It's not 100%, but it's nearly the same fingerprint in all languages. Just imagine this allows you, for example, if you apply this to a search engine, you could type in a Chinese term and search Italian documents and still find the right one without having any machine translation or whatever involved, just natively. So the way how you can make your own machine learning use cases more efficient by this way can be structured in three different groups. In the best case, you can literally take your use case and stop using models at all, getting a model-free solution to it. If you do the conversion into fingerprints, so we have done this with text, for example, for search, as I said before, or extracting the keywords, the most important words in a piece of text, or classifying or slicing. All these typical NLP tasks can basically be done completely language independent and in amazing speed, because it ends up just being sort of the processing of fingerprints. Then there are, for of course more complex problems, models that you can train by using the fingerprint representation as the input. And there you can again take whatever algorithm or mechanism you use to do your machine learning by just changing the representation from a pure number, for example, or a vector, which is more frequent, into a fingerprint, makes you improve the model, make it faster. use much less training data and have it converge faster. So we were able, for example, for a application in the financial sector to make contract data extraction from large contracts with something like 100 examples that are given by a human. Where before that you actually needed thousands, if not tens of thousands of examples. And then there is sort of the highest level, and again in terms of language, it's very obvious where this leads us. It's basically the step into the large language models, and we have been recently showing that by converting the semantic fingerprint into a tensor, which is basically the entity that traditional transformer technology uses to train, we were able to pack so much information into one tensor that we could make the whole model 20 times smaller. So, of course, we are a comparatively small company, so we cannot recalculate models from the big players, but we have shown on smaller models that also use transformer technology that we can shrink a model to 20 times the size, which is quite substantial. So imagine you would use 20,000 GPUs to compute a large transformer model. You would then only need thousands, sort of. Yeah, so it makes a big difference. Just as an illustration, the use of the very same engine. So we literally take the engine that processes text, and when we feed numeric information in the same engine, we can do all of the same functionality also with numeric data. And we have been working recently a lot with sensor data, and we could demonstrate by, if you remember, adding the word fingerprints to produce a sentence fingerprint. If you change the words into sensor values, what you get is the sensor fusion problem that you solve sort of in an elegant way like this. So we have also demonstrated this with a municipal water pump system where we had a time series collection of data of about 1 year of data with 7 events where the pump actually broke. We did not know what the sensor values were representing, so this was really a naked CSV file with 52 measurements per time unit. And in the end of the record, there was a working or broke flag that told us if in that moment it actually worked. We have trained a semantic representation of this water pump system, and what we could show, you see here on the graph next to it, we could show, again, without any model, if we take one fingerprint that was representing a broken state, we could compare any precursor fingerprint to this and measure the overlap of the precursor fingerprint with the broken state. And what we observed is as we approach in the time series to the broken state, there was a bigger and bigger overlap. In that specific case, the increased overlap was noticeable about 4 days before the actual breaking. So this was basically the standard pattern of a sort of supervision model where you want to predict the failing of the system, and that was realized without actually using machine learning at all. So if I come back to my initial concepts about the high energy use of AI, which becomes more and more a problem, one other buzzword is coming up all the time, which is AGI. So people don't yet know if they should fear it or if they should look for it. I do fundamentally disagree with the current concept, at least, of AGI, because what we have shown so far is not a general intelligence. A general intelligence comparable to a human one would need to model the world. And that's not what we have done. We have just modeled the language. I mean, it's cool enough, yeah? But it's not the world. It's just our processed perception of the world that we captured in text, basically, or in language. That is what the model has learned in the first place. But nevertheless, I think there is a big danger in this whole thing. And there my sort of natural science background. I initially studied medicine before I turned into engineering. So what I've learned there in the context of perceptual psychology is that there are certain senses where we don't have an immune system for. So if we see something that we don't want to see, we can close our eyes. But if we hear someone say something, we cannot prevent our brain of processing what has been said. And that is a big problem, because now we have suddenly a big machine that is capable of creating lots and lots of language on one hand, and on the other hand, in learning how we behave and how we are structured, and even optimize that language it generates for our individual brains. So anyone having this technology at their disposal, they can basically send any kind of message to any number of brains. And that can be great in certain contexts, but that can be pretty scary in others. And interestingly, that's a dimension where we don't see lots of policy discussions currently. And so I just wanted to point you at this, that I think that this is quite an important issue that we have to solve at some point. But to close with something positive, I sort of said it already in the beginning. I believe that AI is, at least for now, mainly an interface technology. It is for the first time something that will help us to shrink our mobile phones. One of the reasons why mobile phones have not become smaller over the last 10 years is because our fingers, for example, did not become smaller. But just imagine if instead of swiping on your mobile display, you could have a little box or smaller than this in your pocket, and you just have a knob in your ear and you talk to your phone and you ask your phone stuff, and it answers you, maybe at some point even gives you some display in some eyeglasses. So I think that will change the way how we interact, especially on the internet and in the service environment. It will change as much as the mouse and the Windows system changed the way how we interacted with computers in the 80s. And with this, I thank you.